Hi, Mrs. Stanley here. Let's talk about tangent lines and the derivative. So let's first define the derivative, okay? And we're going to use derivative notation. There are two main concepts in calculus known as the tangent line problem and the area problem. So you may already recall we've been doing tangent line problems a little bit. We've just sort of skimmed the surface of it. And the area problems, which are called integrals. So we haven't even got there yet. Both of these big ideas are related to limits. In the previous lesson, we applied the difference quotient to a function y equals f of x and found a general slope formula. This calculated the slope of a tangent line at any point on the curve, provided the limit exists at that point. Remember this right here? Look down here at the bottom. This is what they're talking about. We did this formula, okay? This general slope formula is also a function and is called the derivative function of f of x, or f prime of x. We've talked about that already. A function that has a derivative at a point is said to be differentiable at that point. So that's what it means. The function is differentiable at that point if it has a derivative, or if we could find f prime of x. Okay? So definition of the derivative. The derivative of the function f with respect to x is the function f prime whose value at x is m equals f prime of x equals the limit of the difference quotient, provided the limit exists. So basically we're taking what we did yesterday, the limit as h goes to 0, of that difference quotient, and we're now letting you know that this basically is what we call the derivative, okay? So there is a note here. The domain of f prime, remember that's the derivative, the slope of the tangent line, which consists of all values of x in the domain of f of x for which the limit exists, may be smaller than the domain of f. So basically we're just making the statement, letting you know that f prime consists of all values of x in the domain of f of x being the original function. But it could be actually more limited. If f prime exists, we say that f is differentiable at x. We did say that up here already, but if f prime exists, we say that f is differentiable at x. Here's what we need to know. There's not really any work on this first page, just in case you're wondering. This right here, this table is letting you know all the proper notation for different ways to say derivative. There are many ways to denote the derivative of a function y equals f of x. Some of the more common notations we will use are shown below. So we have f prime of x. We've already been using this one. Oops, didn't mean to do that. We've got y prime. Notice over here that shorthand, it's brief, but it does not name the independent variable. It doesn't tell us the other variable like f prime of x does. F prime of x lets us know the independent variable is x. And then we have, this is said dy dx, the derivative of y with respect to x. Df dx, the derivative of f with respect to x. And then d dx of f of x. So d dx of f at x, or the derivative of f at x. Don't expect to memorize all of these right now, but just start to notice all of these actually mean the exact same thing. They mean that we're taking the derivative, which means we're finding the slope of the line tangent at the point x equals c. Sometimes we say x equals a. You'll start to notice that there's different notation, and we just sort of use them a little bit randomly. These particular notations, you will find that there are sometimes a pattern. Really it's not that hard of a pattern, but some people tend to use certain ones in different places, and as we go through the year you'll kind of pick up on that. But just start to notice that anytime you see any of these notations, it means the same thing. So let's do some examples. Here we go, the limit definition of the derivative. Graphically, the derivative of a function at a point P is the slope of a tangent line to the graph of y equals f of x at P. We looked at this recently, the slope of the tangent line. You can go back and look at other notes to see that. Numerically, the derivative at a point is the limit of slopes of the secant lines, or the limit of the difference quotient. So remember, they're just talking about this right here. This is the difference quotient. And when we take the limit of it, that's what they're referring to here. The derivative is when we do that. Verbally, a function f is said to be differentiable at a point a, f of a, if and only if it has a defined slope at x equals a. If a function does not have a tangent at a specified point, then the function cannot have a slope there either. So imagine if you're looking at a graph and you can't possibly put a tangent on a specific point, then that tangent can't have a slope and the function can't have a slope there, okay? So these are all just some things that we need to know as we go along, maybe not today, but as we continue in our lessons. So let's look at some examples of what we are focusing on for today. Number 1 says, use the limit process of the derivative to find the general formula dy dx for the derivative of f of x equals 2x squared minus 3x. So we're just going to use this formula, and actually you may think, well, what is any different than what we did in lesson 1? That's okay if you're thinking that. We're just now realizing or stating that we're actually finding the derivative, and we're practicing this other notation. So because I have f of x instead of a y equals, I am going to choose this notation. Again, it doesn't mean that one notation is right or wrong. We're just pointing out that all the notations are used interchangeably, sometimes for different reasons, but a lot of times just from the preference of the person doing it. So we have the limit as h goes to 0, and we're using this function 2x squared minus 3x. Remember, it's f of x plus h. So I've got to plug in here x plus h wherever I see an x minus the original function. And so that's 2x squared minus 3x. I'm going to go ahead right now and distribute the negative. I'm distributing the f of x plus h minus f of x. If I lost you there, go back and look at the formula. And it's all over h, right? So let's go ahead and simplify the information on the top. So when I bring this all through, I've got the limit as h goes to 0 of 2 times x squared plus 2xh plus h squared minus 3x minus 2x squared plus 3x all over h. Now, because I don't want to have to write this out all again, I'm going to change my pen color and show you. I'm going to distribute this 2, and it's going to be 2x squared plus 4xh plus 2h squared, and this is going to be canceled out, or it's gone because I distributed, okay? So I just did that so that I can do my cancellation, right? So here we go. I've got 2x squared minus 2x squared. I've got negative 3x and positive 3x. These other terms have an h, 4xh plus 2h squared, right? I'm starting to question myself here because I'm going, I feel like there should be another term, and guess what? Look what I did. Look way back here. 2 times x plus h squared minus 3 times x plus h. I left it out. So let's go back and fix that. I want that same pen color, so let me go back to it. This should be 3x plus h. So I'll pause so I can fix it just to not make the video longer, but make sure you know why I'm doing it. So I put that in there, and I've got the limit as h goes to 0. Since we already multiplied this out one time, I'm just going to rewrite the part that we're keeping. 2x squared plus 4xh plus 2h squared minus 3x minus 3h minus 2x squared plus 3x all over h. Now let me double check that again. Okay, now let's see what cancels out. We've got the 2x squared minus 2x squared. We've got the negative 3x plus 3x. And now I have 3 terms with an h. Now, how did I know before something was wrong? I just felt like there was not much left. There was like just a feeling like, I feel like there should be something else. And so I started looking back, okay? It's as you do more problems, you'll start to just notice like, oh, I feel like that should have had more or less. Sometimes you're like, why am I doing so much work? Let me figure out what I messed up. So I'm going to go ahead and factor out my h so that we can see it. I've got 4x plus 2h minus 3 all over h. And what's going to happen? We know our h's are going to cancel out. And we're going to be left with the limit as h goes to 0 of 4x plus 2h minus 3. Plug in your 0 and you get 4x. 2 times 0 is 0 minus 3. So 4x minus 3 is our dy dx. dy dx equals 4x minus 3. Let's come down to the next one. Number 2, we're doing the same thing. They just use a different notation. Given y equals x squared minus x, use the definition of derivative to find f prime of x. I'm going to zoom in just because I've started to do that more often because I like it better. So here we go. We're doing f prime of x. And we're still using the same formula. Think about it. Remember, we've said it's the limit as h goes to 0 of the difference quotient. So let me not make any mistakes this time. Y'all pray for it right now. Pray that as you watch this video, you'll see that I was successful in not making any mistakes. X plus h squared minus x plus h, right? I could have went ahead and put that distribution out, but I won't. Now I am going to, though, because we got to do minus f of x, so it's just minus x squared, and I'm going to put plus x instead of dealing with the parentheses over h. So there's our function. Then we can just do the next step to get all those exponents and such distributed out. So x plus h becomes x squared plus 2xh plus h squared minus x squared plus x all over h, correct? Now let's see what cancels out. I've got an x squared and a minus x squared. I've got a negative x and a positive x. And I have 3 terms left and they all have an h. So let me go ahead and rewrite now the limit. As h goes to 0, I'm going to pull out my h, 2x plus h, and that h comes out, so I just have minus 1 over h. Don't forget it, that minus h doesn't suddenly disappear. H divided by h is 1, not nothing. So these h's will cancel out, and we are left with the limit. How did I get blue suddenly on my screen? Sorry about that. 2x plus h minus 1, which means f prime of x equals 2x minus 1. Because remember, when we put a 0 in for the h, that'll just disappear. So here we are. F prime of x equals 2x minus 1. You could go back and think about these. Look at the 2 different functions. These f of x's are both polynomials, and so the domain is all real numbers. And then their derivatives are actually linear functions, so it's still all real numbers. We haven't had to deal with any limits on our domains so far. Let's keep going now to the next page. Alternate forms of the derivative. What you're going to see here is that we have 2 different formulas that look very similar to the limit with the difference quotient, but they're slightly different. Look here. The numeric value of the derivative at a point x equals a. This is what makes it different. At a point x equals a is also found by f prime of a, or the slope of the tangent, equals the limit as x goes to a of f of a plus h minus f of a over h, or by f prime of a equals the limit as x goes to a of f of x minus f of a over x minus a, provided the limit exists. For all a for which the limit exists, f prime of x is a function of a. So basically, this is 2 other formulas. If you look at them, they're kind of similar to the difference quotient, taking the limit as h goes to 0, but just slightly different. And unfortunately, you do need to be able to recognize them, because when you take the AP exam or any other calculus exam, you will see them used. And sometimes you might see them used in science classes or other things, and you just want to be able to go, oh, that's one of the derivative formulas. So let's do a couple practice problems using these formulas. Use the alternate form of the derivative to find f prime of a for f of x equals square root of 3x plus 1 at a equals 1. But do notice that's the key. It's at a specific point. It says the numeric value of the derivative at a point x equals a. That is like a qualification. We can't just use this formula anytime we feel like. We're using it because we're at a specific point. The first thing we need to do is calculate what is f of a. In this case, a is 1. So we plug it in. The square root of 3 times 1. 3 times 1 is 3, plus 1 is 4. Square root of 4 we know is 2. Now why do I need to do that? Because look, both of these formulas, no matter which one I use, I need to know f of a, and in my specific problem, a equals 1. So let's look at this now using the formula. F prime of a equals, did they tell us which one to use? No, we get to pick. So I'm going to use this one. I'm going to do the square root of, you know what, I changed my mind. Since it has a square root, why not just use this one? We know what a is. It's a square root. We won't have to deal with square rooting x plus a and all that stuff. So let's do that. We have f of x. That's just 3x plus 1. Minus f of a. We already said f of a is 2. Minus 2. over x minus a. Okay, x minus 1. See, this is already much easier. But we do have the problem of that square root. We can solve that pretty easy, can't we? Let's do the conjugate. We're going to multiply top and bottom by the conjugate, 3x plus 1 plus 2 over the square root of 3x plus 1 plus 2. I apologize for not reading the square root the first time. So here's what we're multiplying to simplify our problem. So, and we can actually stop saying f prime of a now. We can say f prime of 1 because we know what a is. We don't need to write a. What happens on the top? Square root of 3x plus 1 times the square root of 3x plus 1 is just 3x plus 1. And then we've got our middle terms are going to cancel out. Remember, that's the whole point of the conjugate. So negative 2 times 2 is negative 4 all over this big long thing. Let's write it out. Square root of 3x plus 1 plus 2, close parentheses. Now, what's going to happen there on the top? We have 3x plus 1 minus 4. Well, that's going to help us out a lot because what happens here? This is 3x minus 3, which is what? And oh my goodness, you know what else I just noticed? I thought I was going to make no mistakes. I left something out here. Look, let's move this over. What did I forget, y'all? Anybody figured it out already? I left out my limit notation. I need right here my limit as x goes to a. Good gracious. I thought I was going to do a whole problem without having to fix anything. At least it was easy enough to fix on my digital form here. Let me write that in. Now, just so you know, this is very important. If you leave out that limit notation, you have changed the entire problem, and they will ding you on the AP exam. It'll get points off, even in class. If we're taking a test or something, you're going to get dinged for that. So it is an important matter. So here we go. Moving on again. The limit as x goes to a. 3x minus 3, I'm going to go ahead and factor that. That's 3 times x minus 1. Why am I doing that? Look at the denominator. We've got something now that we already know is going to cancel out. 3x plus 1 plus 2. Close that parenthesis. What's going to cancel out? This x minus 1. And we are left with the limit as x goes, see, I don't even need to write x goes to a. X goes to 1. We know what a is. We can stop just calling it a. Of the square root of 3x plus 1 plus 2. And now I can plug in, right? I can plug this in, and we know it's 3 over the square root of 4 plus 2. The square root of 4 is 2. It's 3/4. So I can now state clearly that f prime of 1 equals 3/4. Right? Okay. So that was the benefit of having an exact point. You can work it out a little bit more easily because you don't have to have all the x plus h's and stuff. So here's some more notes. This isn't really any work, but let's read through it real quick. Observations for using the derivative formulas. When finding the derivative at a point, there are two approaches. You can either find the general formula first and substitute your x value, or you can substitute the x value from the start. So just keep that in mind. All it's saying is that you can plug in first and then simplify, or you can do the x plus h or whatever you're using and plug in at the end, okay? And then also down here we've got question types and equivalent terminology. The point of this part is just to help us see when might we use a certain formula. If you're given 1 point, a and f of a, you're given only 1 point, you are finding the instantaneous rate of change at x equals a, which is the slope of the tangent line. Remember, instantaneous rate of change is the slope of the tangent line, which is also called the derivative at x equals c. This is the derivative at a specific point, okay? This is your formula for that, okay? Now, on the other side here, we've got if you are given 2 points, a f of a and b f of b, you are finding average rate of change on the interval, the closed interval ab. This is the slope of the secant line. So remember, the instantaneous rate of change is the tangent line. The average rate of change is the secant line. Look how much simpler the formula is for secant. Well, that's easy because we have 2 points. We can easily just calculate the slope, right? When we're doing the instantaneous rate of change, now we don't really technically have 2 points. We only have 1, which is why we've got to do a limit. Okay, let's look at the next example. Find the slope of the tangent line. Okay, this is a tangent line, so instantaneous rate of change, or we're finding the derivative. Y at the sorry about that. Find the slope of the tangent line to the hyperbola y equals 2 over x at x equals 3. I've got a point. Okay. Now looking here in question A, they're telling me which formula. They say using m equals the limit as x goes to a of f of x minus f of a divided by x minus a. So the first thing I need to know is, what is f of a? Well, a is 3, right? What is f of 3? Well, it's 2 over x is the function. Well, that's going to be pretty easy. F of 3 is 2 over 3. So now we can come down here to use our formula. Okay, I've got... let me write the first part. M equals the limit as x goes to a. What's a? It's 3. Of f of x. F of x is 2 over x minus f of a is 2 over 3 over x minus a, which is 3. So here is our equation, and now we just need to work it out. Here we go. This limit as x goes to 3. What do we need? We need a common denominator. We've got x and 3, so let's multiply everything by 3x, okay? We can just multiply the top and bottom by 3x, and that is going to give us, well, when we do the 2 over x, the 3 times 2 is going to give us 6. And we've got 6 over 3x minus 2x over 3x. And on the bottom, I still have x minus 3. So I didn't multiply the top and bottom of this big fraction, okay? I just multiplied the top and bottom of the 2 top fractions, okay? Now I'm going to simplify this down. How can we simplify that? Well, remember, you multiply by the reciprocal. If my arithmetic has confused you, this is a separate issue and you'll need to let me know, or just pause the video and do the fractions yourself and think it through, and it'll all work out, okay? So we've got the limit as x goes to 3 of 6 minus 2x over 3x times x minus 3. Well, I can divide out a negative 2. And what's that going to do for me? That's going to give me negative 2 times x minus 3 over 3x times x minus 3. What happens with my x minus 3's? They gone. So we are left with the limit as x goes to 3 of negative 2 over 3x. Now remember, they gave us the value that we're using for this problem, right? Negative 2 over 3x as x goes to 3. So we just need to now plug it in. M is going to equal negative 2 over 3 times 3, which equals negative 2 over 9. So there is our answer. Now look what's going to happen. On B, they want us to do the exact same problem, just using a different formula. So we still have y equals 2 over x. Rewrite it over here if you need it. And we still have a equals 3. And so that still tells us that f of 3 equals 2 over 3, right? That was all of our information? Yes. So let's go ahead and do this problem now using this particular formula, okay? So in this formula, we have that the limit as h goes to 0 of f of a plus h. So I've got to do 2 over a is 3 plus h minus f of a is still 2 over 3. So that's easy enough. All over h. So this one looks a little bit different, but not really too much. On this one, because of the way that the h is just in the denominator, I'm going to go ahead and just kind of separate that out and deal with the 2 numerator fractions first. I'm going to pull out my 1 over h and then have it written like this. I've got 2 over 3 plus h minus 2 over 3. I'm going to go ahead and multiply to get my common denominator. That would be multiplying by 3 times 3 plus h. So on this side, I'm going to get 6 over 3 minus 2 times 3 plus h over 3 plus h, right? So all I've done is dealt with these two fractions on top to get common denominators so that I can simplify. So what's going to happen here? The limit as h goes to 0, I still have my 1 over h times, let's simplify this fraction, 6 minus 2h over 3 plus h. Notice I just distributed the 2 and I put my two numerators together. Now what's going to happen here? Notice this. 6 minus 6, that's going to go away. This h and this h. This is a multiplication now, right? There's no more adding and subtracting here. So I have h and h. What am I left with? Whoops. I've got the limit as h goes to 0 of, oh, look, I wrote my denominator wrong. Did anybody notice that? This should be 3 times 3 plus h. I was about to say, it can't just be 2 over 3. That would be too simple. It's negative 2 over 3 times 3 plus h. And what happens when I plug in my 0? Well, I'm going to get negative 2 over 3 times 3 plus 0, which is negative 2 over 9. Notice I got the exact same answer that we got up here on A, negative 2/9, negative 2/9. The reason they had us do this with the same problem is just to show that it works out exactly the same. You can just decide if there's a specific one that you like better. So verbally speaking, you are finding all of the following, okay? Number 1, we've got the slope of the tangent line to f at x equals a. Number 2, the instantaneous rate of change of f at x equals a. Number 3, the derivative of f at x equals a. Number 4, the limit of the difference quotient of f at x equals a. These are all the exact same thing. These are different ways of saying what we just did. We just got to get used to this vocabulary. So again, keep yourself some sort of note page where you can write these kind of things down. Maybe do some, decorative notes, whatever works for you. Let's go to the next page and look at this graphically. Understanding the derivative graphically. This part is not necessarily like new information. It might be a little bit weird. I almost thought about skipping it just because I didn't want to create confusion. But let's go ahead and give it a try. Grab some colored pencils and a ruler if you've got it. If you don't have colored pencils, just use 2 different colors of pen or a regular pencil and a pen. It doesn't matter. It says blue and red, but you can do whatever. It's fine. That part's not something to worry about. The graph of the function y equals f of x at right is differentiable on the interval a plus h. Notice a is here, a plus h is here. Okay, these are our x values. It is differentiable. So we're going to answer some questions. Use the expression in column 1, that's down here. Using this expression, state whether the expression represents a length or a slope. This is the part that I felt was maybe a little bit confusing. Why are they calling it a length? Because if you look at the very first one, it says f of a. I wouldn't think of f of a as a slope. But again, let's not die on a hill. If you've ever heard that saying, it's not a big deal. The primary thing is just noticing, are we taking a slope or not? And the opposite of the alternative that they're calling it is a length. Here's why. Looking at number 1, f of a would be this point right here, correct? What they're calling the length is this line, the distance from a up to f of a. They're calling that a length instead of a slope. The key thing to notice is it doesn't have anything to do with the derivative. What is f of a? Well, it's actually quite simple. I think that we all know what it is. F of a is the value of f of x at x equals a. That's all it is. So we can just write that down. There we go. The value of f of x at x equals a. Why am I using a capital F? Because that's what they used up here. No worries. The value of f of x at x equals a, it's a length. Okay? The main thing to notice is if you're asked for f of a, you're asked for the specific value. And this is why I don't necessarily like that they're calling it a length. But let's just focus on the fact that it's not the derivative. It's just a point, and we can calculate it if we know what a is. Number 2, f of a plus h. Well, if we've got a plus h right here, Then we know that this is f of a plus h, right? So this time they're talking about the length here. Now for some of you, you might be going, yeah, I totally get why they're calling it that. It's not a problem. Sometimes our brains just work differently than each other. I still get the point. The point here is, can we notice what things are related to the derivative? So what is this? This is the value of f of x at x equals a plus h. Here we go, the value of f of x at x equals a plus h. That's easy enough. Let's look at the next one. F of a plus h minus f of a. You might start to think, oh, this is looking more like the derivative, but this is not divided by h. There's no rate of change here. There's no limit. So we're still just actually looking for a length. In this case, I would say that I agree that it's a length. The f of a plus h minus f of a, that's basically just the distance. And see here, I would want to change colors. Let me go the other way. If we're looking at it, if this is a plus h, or I'm sorry, f of a plus h, and this is f of a, let's do it over here. This is a plus h. This is f. Goodness, I apologize. This one that I first drew is f of a plus h. The one down here that's purple mark, this is f of a. So the distance for number 3, this would be f of a plus h minus f of a, right? And I don't think that my drawing is very accurate, but hopefully you can tell. I think maybe I put this one too high. It should be a little bit lower, like down here. Okay? Either way, it's the same. So this one, I agree, is a length. It makes more sense to me. I'm not saying I disagree on the other one. It was just a little bit harder for me to grasp what they meant by a length. To me, I think of f of a as a specific point, but that's okay. This one is definitely a length. Let's write down what would be a terminology for it. Here we go. The difference in y values for f of x between x equals a plus h and x equals a. That's how we could describe it. It's the difference in the y values. Let's look at number 4. 4 just says h. What is h? Well, interestingly enough, this one is right here. We have h, the distance between a and a plus h, right? If you wanted to not have it on there on the graph that they already have, you could put it down here, but they've already labeled it for us, so why bother? So for me, I would just mark right here. This is number 4. Okay, so it again is a length, right? This is a length. What is it representing? How can we put it in terminology? Okay, so this one is the distance on the x-axis between x equals a and x equals a plus h. There is a word, I think, that we would use more in science. This is called the displacement. The change on the x value can be called the displacement. Look at number 5. Suddenly, we finally have something that looks different, right? I'm going to use a red pen because up here it said a red pencil or pen, whatever you want to call it. Number 5, f of a plus h minus f of a over h. This one we said the other day, we've got to learn to call this, I almost wrote it wrong, the difference quotient, right? And what does the difference quotient represent? The slope of the secant line. So this has to be a slope because we know that formula. That's the difference quotient. So coming up here, f of a plus h minus f of a over h. That's this right here. This is number 5. And how could we write it in terminology? Here we go. The average rate of change, AROC, of f of x on a plus h. I'm going to also make a note that this is the secant line. This is the secant line to the point x equals a. Now, what do we see about the next one? What's the difference between 5 and 6? We don't even need the graph, but we could look at it. Between 5 and 6, we're taking the limit. The limit of the difference quotient is the slope. It's the slope of what? The tangent line. This should be jumping out at us, hopefully. It's the tangent line. If we come back up to our diagram, f of a and a is right here. So the instantaneous rate of change, the limit of the difference quotient, the tangent line, it's all right here. It's the slope of the tangent. So this is number 6. We're finding the slope of this line. And I might not have drawn that very well, but hopefully you can tell what it means. Here's our terminology. Okay, it's the instantaneous rate of change, IROC, of f of x at x equals a. I am going to make one edit right here. It's the tangent line slope. It's not the actual tangent line, right? It's the slope of the tangent line. It's also what? The derivative. That's the word that we're learning today. This is the derivative. And finally, f prime of a, that's also a slope. And the good news is we're going to say it's the same as number 6. They were testing us. Look, the limit as h goes to 0 of the difference quotient is f prime of a. We don't need to rewrite all of that. It's exactly the same. So let's go to our last page of notes for this lesson. Understanding the derivative symbolically. Oftentimes you will be asked to extend your knowledge base for operations in calculus where you need to recognize functions, procedures, processes, theorems, and properties. You might also need to decompose or deconstruct mathematical operations symbolically. Here is a sample of such instances. So this is what we're going to do. On number 6, each of the following expressions represents the derivative of some function y equals f of x for some value x equals c. Identify the function y equals f of x and the value for x equals c. So basically we are working backwards. They're telling us that they have already set this up into one of the formulas for derivative. It could be the limit of the difference quotient. It could be those two alternate forms. If you need to find it on your notes, I'll scroll back so you can see how far back you need to go. Go back on your notes to these two formulas. We're looking at these two formulas plus the limit of the difference quotient, okay? So use those. These, you might want to pull this page out to look, or screenshot it if you're using a tablet or something like that. Unless you've already got them memorized, then you're good to go. So looking at A, what formula might this look like? Well, we've got some sort of x plus h, but it's actually still h. And the x is 4, right? So this one looks like some sort of f of x. And this one is just a value, which means they probably used f of a. Okay, so this is useful information for us because we can see there's a square root. So the question that we're asked first is identify the function y equals f of x. What is f of x? Well, let's see. If it was the square root of x, what would the c value be? Think about the formula f of x plus h minus f of a over h. This is the way I'm kind of looking at it. And actually, I would say one thing that might have actually confused you there. Change this x to a plus h. Because now you can see, if my function is square root of x, what would be the square root of 4? 2, and that matches right here. If f of a, if I'm doing minus f of a, and a was 4, then f of a would equal 2. So this is good to know because it says my x equals c. So what I'm finding out is that c equals 4. How did I know that? Because the square root of 4 equals 2, and that's what's right here in the function. Okay, let's try another one. This one might be a little harder because you might not remember the functions with e. This is e to the power of cosine of pi plus h minus e to the negative 1. Well, the strange thing is, somehow we know that they got a negative 1 here, but originally there had to have been a cosine because these two things have to match in some way. What's being added to h? Pi plus h. Well, here's something to think about. What is cosine of pi? If you remember on your unit circle, cosine of pi is negative 1. If you start at 0, 0 degrees is also 0 radians. That's equals 1. Cosine of 0 is 1. Then you go to pi over 2 up at 90 degrees. Then over at 180 degrees, you're at cosine of pi, and the x is negative 1. Okay, so how do we go from this to this? Well, that makes sense because if this function is e to the cosine of x, and x, or in this case what we're calling c, is pi, then it would make sense that this right here is a plus h, and this is f of a. Sorry, this is f of a plus h minus f of a. A or c is pi. That's why I said earlier on when I was talking about notation, you've got to get used to the idea of a or c being used for the value of the x. Let's keep going. Look at c. Tangent of 2 times 2 plus h minus the tangent of 4. Well, what I notice right away is that 2 times 2 is 4 right here. And I know that this plus h gets thrown in there all the time. So that makes me go, okay, it must be the tangent of 2x. And if c equals 2, well, then what would I get if I needed f of a or f of c? F of c would be the tangent of 2 times 2, which is 4. And the tangent of c plus h would be, the function of c plus h would be the tangent of 2 times 2 plus h. So that works, right? Now, I'm telling you, you should probably pause and do this on your own. D is probably not the one that you should pause. I'm not even going to try to explain this, except for just for you to notice the 1 over h is just that they have pulled out the h from the denominator, so you don't really need to worry about it. And then we have a natural log of 6 plus h and a natural log of 6. Okay, so looking at the natural log, you've got to remember your rules. So if you remember the natural log of 6 plus h minus the natural log of 6, this would simplify to the natural log of 6 plus h over 6, right? You may not remember that all the way back in Algebra 2, but that is how they simplified this. So this is actually much easier than it looks. We're taking the limit. We've got the 1 over h. So f of x is the natural log of x, and c is 6 because it's right there. Okay? So that's how we got the answer to that one. It's based on the rules for simplifying natural logs. Okay? Now coming to E, this one, now let's remember our formulas. We have the one formula that is f of x plus h minus f of x all over what? All over h. The other formula is f of x minus f of a all over x minus a. Well, notice here we've actually got some subtraction in the bottom instead of h. So that is our clue to let us know that we're not using this formula anymore. We're now using this one. So let's keep it there to just keep it in mind. So that means this first one is just our f of x. That's what we were looking for. What's f of x? Well, now we know it's x minus 1 squared. And on the bottom is x minus a. Where's a? Right there. Since it's a minus 3, that means a, and we're calling it c because they called it c, is 3. We can test that out. 3 minus 1 is 2. 2 squared is 4. That's what they got right there, right? So that works out. Look at the next one. Again, we've got x plus 2 in the denominator, and there's no h. That tells us we're still using this formula. So f of x is right here. F of x equals the cube root of x minus 6. And then what's a? Well, they tell us right here. But what happened? It's a plus 2. So what does that tell us? Because it's supposed to be x minus a. That means that a, or what we're calling c in this case, is negative 2. Test it out. What would it be if we had negative 2 minus 6 in a cube root? It would be the cube root of negative 8, which is right here. It still works out. So this is our final answer. I hope that made sense. Give that a little more thought and go ahead over to the practice problems.